Okay, here's the deal. I've been telling myself for a while that I would make a video about global warming. I was going to put some of my science background to good use and talk about topics that I've been talking about for a while online, in online forums, etc. And rather than repeat myself, I can start actually pointing to videos that I make. So I had some time today, and seeing how it's an uncharacteristically warm April, particularly end of April, I thought I would start here today. So beautiful day here, and it's a good place to start with a good friend, the sun. So to the studio. Okay, let's see what we got here. So here is a typical Gaussian distribution of the energy that we get from the sun. That's 100% of the sun energy is in this chart right here. This is in watts a square meter, so that's the relative power. And here is the spectrum, the wavelength in nanometers. So you can see the bulk of it is in here is the visible spectrum that humans can see, and it's your colors of the rainbow. UV to red. Red, orange, yellow, green, blue, indigo, violet, or Roy-Gabib from the colors of the rainbow. So we see that in the rainbow coincidentally because this white light is split into its various color components as it goes through the prism of the little droplets of water. Or if you go through a crystal, you can see that it just happens to be over the hump here with the most intensity. So obviously humans, like other animals, are land-based, and they utilize the peak radiation, light being a radiation, to see. So the vision system is set up only on this small little component here. And it's actually, I think this is exaggerated, so it's even narrower than this. But you can see here, as you go into violet, is the most violet color being on this side. After that, it's UV, and you will not see that. It will burn the skin, UVA, UVB, UVC, as you go in this direction. And if you head over in the other direction, if you think of the reddest color you could see, possibly more red than that, you will not see it with your eye, but you could feel it with your skin. So you can feel the heat from a hot surface. It's called black body radiation, and these are wavelengths coming up past like 800 nanometers plus. So this is the infrared spectrum over here. Now this is watts per square meter, so that's I think that's a kilowatt per square. Let me see if I can find another chart. Watts a meter squared in nanometer, right? Okay, similar sort of chart here. Okay, here we got black body spectrum right here. So that is the spectrum. So when you look up at the sun, which I wouldn't advise, this is the spectrum of your light. Now, infrared. Infrared is responsible for global warming. That's the heat component. And certain gases are more absorptive of infrared radiation than others. So let's have a look at that next. Okay, so now that we've looked at this sun emission spectra and we understand the nature of that spectrum, this is another chart here that I found, you can see that the infrared spectrum is about 51%, so we can't even see this area. Not visible, but it is the infrared, so any energy from here captured is going to be contribute to heat. So what is heat? What is the nature of heat energy, and how does that all occur? So let's have a look. So this is contrary to a lot of people would think, that most of the air is actually nitrogen, followed by O2, and then you've got these trace gases here. So not much, just a little bit of water and a few other trace gases. So it's not even detectable. They're so small, parts per millions, that they don't even register in comparison to O2 and N2. So that's the first step, right? Let's have a look at this, maybe we can understand that some by parts per million, some gases, not very important. So heat causes this sort of Brownian motion. These are molecules excited by heat. And the energy goes into those molecules and they dance around like that. Don't worry about this yellow ball, that's something else. Let's have a look at some animation GIFs. More energy in the system causes these things to bounce around. But on the molecular level, here's an example of some water types of heat that gets absorbed in the actual molecule itself. So that's a H2O, you got your helium, your hydrogen, and your two oxygens here. And infrared light hitting a water molecule can excite the molecule to jiggle around like this. You've got the semantic stretch, asymmetric stretch, bend, and these types of between the bonds, the wavelength happens to be in a size that is good at exciting the molecule in this nature. Simple as that. So CO2, here's another animation I found. It is the perfect size. This, and I'll get to methane as well, CH4, are very good size molecules for infrared spectrum to absorb and then re-emit heat. There's your carbon dioxide. So if you have a look at some, so if you remember back from our heat chart, and what nanometers it was, the infrared's kicking in around here, O2 just being outside the spectrum, and all the 50% of the radiation that would be across here is absorbed by H2O, and CO2 is in there. The other gases are basically invisible to, here's another chart, let me see if I can find it, this one, right? CO2 is a strong greenhouse gas, known for, this is not new science, this is 100-year-old science here. CO2 is a very good absorptor of infrared. Now this is a particular big problem when you can see the increases in CO2 in the last industrialized world has been spewing out massive amounts of CO2, obviously by fossil fuel burning. So all of that carbon, once stuck in the ground, not part of the carbon cycle, is trapped as coal after millions of years of being taken up by forests and microbes in the ocean, and falling to the bottom of the ocean and being buried under sediment and under the earth and being trapped there and out of the carbon cycle, has now been released back in the atmosphere. You dig it up, you burn it, and the carbon that was once in the coal is now in the air. Simple as that. It's quite easy to, once you sort of start thinking about it. So this whole clean coal bullshit, not possible, because, you know, the very nature is you have to burn it, turns into a gas. And the volumes of gas from coal is completely 100% of what's coming out of the smokestacks. So they are being released into the atmosphere. So let's next have a look at what does it mean to have extra? Like, what does it? How does that measure? How many parts per million of CO2 contribute to what degree of temperature absorption extra in joules? Let's look at the energy. Let's do that as the next video, which I might have to split into another video because this one's probably already too long. But hope you found my initial explanation interesting enough, and I may continue to the next video. Thanks for watching.